Hey, today I would like to show you some of the work we are doing, building up a time series of hydrography and biogeochemical parameters north of Svalbard, and how we think the sea ice cover is influencing much of the internal variability. On this slide, you see a composite satellite image of the Arctic Ocean. It's very wide. You see the sea ice cover in the central Arctic, but around the edges there's open water and some clouds. In the orange circle is Svalbard, and clearly west and north of Svalbard there is darker. It's indicating less ice, so something is preventing the presence of sea ice. That's where a large part of the Atlantic water bringing heat to the north enters the Arctic. Why is this Atlantic water so important? It's because it has a huge influence on the structure of the Arctic Ocean. So in this schematic, Carmack and Melling contrast the Atlantic and the Pacific side of the Arctic. And as you can see, there is no or little sea ice on top of the Atlantic water, whereas there is some ice over on the Pacific side. And that is partially because Atlantic water is so warm that it melts sea ice or prevents ice formation. Now this is of course very simplified, it's a bit more complicated than that. So what we try to do is to find out more about the role of Atlantic water, both regarding how its heat influences the surface of the ocean and the sea ice cover, but also its role in providing nutrients for the Arctic ecosystem. In the vane project, we put our sensors moored to the seafloor to measure temperature, salinity, currents and other parameters at different locations on the continental shelf and slope north of Svalbard in the middle of the Atlantic water inflow. This is what that looks like on board. Here we are deploying such a mooring in November 2019. So all train wheels serve as anchor weights, and attached to them on a rope are the sensors. If all goes well, they kind of stand upright in the water and record measurements until we pick them up again a year or two later. Here's an example of part of the dataset, which shows temperatures recorded over a year in 2012 to 2013. The Atlantic water inflow is characterized by high temperatures, around 2 to 4 degrees centigrade, and we clearly see a seasonal development from autumn to winter, spring and finally summer. We found two very distinct periods in our data. In autumn and early winter, there were periods of very large heat flux from the Atlantic water to the surface, which prevented sea ice to form, or melted sea ice that was blown in by the wind. Eventually, sufficient ice melted to form a cold and fresh layer above the Atlantic water, protecting blown-in sea ice and enabling new ice forming in spring. There's a lot of variability from year to year, both in Atlantic water volume and heat, and in wind and sea ice transport. At one mooring location, we now have a 7-year time series of ocean properties, and the data show that, yes, warm water temperatures often occur at the same time as low sea ice concentrations, and cold temperatures often with high ice concentrations, but there are many episodes where this relationship doesn't hold. Instead, wind-driven sea ice motion leading to ice advection towards the vane region dominates the variability in sea ice presence during the past 10 to 20 years. It is a complex interplay between the ocean and the wind that determines sea ice concentrations north of Svalbard, and with that also exchanges between ocean sea ice and atmosphere. Sea ice is a major factor in the Arctic climate system, not only because of geophysical processes, but also because of the impact on the ecosystem. Persistent sea ice reduces availability of light for photosynthesis and phytoplankton growth, especially in the presence of snow. It also limits wind-driven mixing, which is important for the resupply of nutrients to the upper ocean, where light would permit primary production. As moorings require regular science cruises for recovery and redeployment, we use these cruises to collect further hydrographic data and water samples to measure nutrients, chlorophyll A and other parameters on transects along the mooring line. Now we are analyzing this dataset to investigate what drives variability in nutrient levels and distribution and primary production in the region. So chlorophyll A gives an indication for the amount of phytoplankton in the water. And the concentration of chlorophyll A varies by season, but also from year to year. And there the sea ice cover is a major factor. But it's not quite as straightforward as a lot of ice equals low chlorophyll levels and little ice means a lot of chlorophyll. Instead, the timing of sea ice coverage, the impact this has on the underlying ocean and the access to nutrients seem to play an important role. We are now working on developing a better mechanistic understanding of the processes. There's lots more to figure out, plus exciting new data to integrate, so stay tuned for updates.